GCE Advanced Level Chemistry Practical Series, experiment number 21. Observing the colors of copper, nickel, cobalt salts with hydrochloric acid and ammonia solution. In this practical, we aim to provide the necessary knowledge to explain the fact that D block elements can form coordination compounds, and to prepare a few complex compounds, and to state that the hydrated ions of those complex compounds are colored. Now, it is essential to understand in this experiment that the elements found in group 3 to group 12 are collectively classified as D block elements. Now let's move on to our next slide. So in period 4, we have these 3D elements. So whenever we are talking about 3D elements, 3D elements are elements where their highest energy electron is getting filled into a 3D subshell. So we have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. So then we come across another term called transition elements. Now, one of the things that a lot of students get confused about is they think that 3D elements and transition elements are both the same. However, by definition, they are different. When it comes to 3D elements, any element that has their highest energy electron filled to a 3D orbital is referred to as a 3D element. However, transition elements are having a different definition. So let's take a look at that. D block elements containing incompletely filled D subshells at the elemental state or with the ability to form at least one stable ion containing incompletely filled D orbitals or D subshells are called transition elements. So the definition of transition elements state that you should have incompletely filled D subshells. When it comes to transition elements, you have to make sure that they contain incompletely filled D subshells either when they are present as an element or in one of their stable ions. So if these 3D elements are forming a stable ion that contains incompletely filled D subshells, or if they have incompletely filled D subshells when they are present as an element, we can consider them to be transition elements. So therefore, they say D block elements producing ions only with D0 and D10 electronic configurations are not considered to be transition elements. They are considered to be non-transition elements. So if you have completely filled D orbitals or if you have completely empty D orbitals, at that point we cannot consider those elements or the ions forming that electronic configuration to be a transition element. So zinc and scandium are D block elements. The last electron is filled to a 3D orbital, so therefore they are considered to be 3D elements, or we can call them D block elements. However, zinc is not considered to be a transition element. It is a non-transition element. The main reason for this is, as an element, zinc has completely filled D orbitals, as well as when you are forming a stable ion using zinc, we form zinc 2+, and even in its stable ion, it does not contain incompletely filled D subshells. So therefore, zinc will not be characterized as a transition element. So all of the 3D elements are not transition elements. we can very clearly see zinc is not a transition element. But all of the others, from scandium to copper, all the 9 elements that you find from scandium to copper are transition elements. Only exception is zinc. So scandium is considered to be a transition element, mainly due to the fact that when scandium is present as an element, it contains incompletely filled d subshells. So therefore, scandium is falling under transition elements. Now, with that, let's move on to observing some colors of the aqueous ion solutions of these 3D elements or transition elements. So over here we can see different colors: purple, green, pink, yellow, brown, blue. All of these colors are normally observed when transition elements are present in the aqueous medium. So if you take titanium 3+, vanadium 2+, and chromium 3+, aqueous ions, they form complex ions that are going to produce a purple color. And we have vanadium 3+, nickel 2+, and iron 2+ ions. They are forming complex ions with water that are going to have a shade of green. And we have cobalt 2+ and manganese 2+ that are going to be producing pink color solutions. But keep in mind, students, now cobalt 2+ complex ion that it forms in water gives off a very observable pink color. However, that is not the same with manganese. Manganese 2+ aqueous ions do not necessarily form a very observable pink color. It is in fact quite low in its color intensity. Mn2+ aqueous ion solutions are normally observed near colorless. So this pink color is normally referred to as a very pale pink color. You do not necessarily observe it very clearly in the lab environment. And we have iron 3+, so iron 2+ is pale green in color as mentioned earlier, and iron 3+ aqueous ion solutions form this complex, which is yellow brown in color. And we have our copper 2+ ion solution, which is going to be a pale blue color solution. So this is just a rough idea about the different colors of some aqueous ion complexes that some of the transition elements form. Let's move on to our next slide. In this slide, we can see some important points that we should keep in mind. So aqueous ions of scandium 3+ are colorless, despite it being a transition element. So normally, students, for a transition element to produce ion complexes that have a color, it should have partially filled or incompletely filled 3D subshells. So if you take a look at scandium 3+, although it is considered a transition element, it does not contain any incompletely filled 3D subshells. So therefore, even when it is forming a complex ion with water molecules here, you do not observe a color. So the aqueous ion solutions of scandium 3+ are going to be colorless. It's a very important observation to keep in mind. And then we have zinc. Obviously, we know now that zinc is not a transition element, meaning it does not contain 3D subshells that are incompletely filled when it is an element or when it is forming a stable ion. So even when it is forming a zinc 2+ ion, its 3D subshell is completely filled. So it cannot actually produce any colored compounds. So zinc 2+ does not produce aqueous solutions with any color. So zinc 2 plus is going to form complex ions that is going to have no color in them. So this is going to be colorless. So zinc, of course, is something that you can keep in mind, but very important to notice that although scandium is considered a transition element, aqueous ions of scandium 3 plus is not going to have any color. They are going to be colorless. In this slide, we are going to be looking at few other ions that are not going to be producing colored solutions in aqueous medium. So first, we have here few D block elements that are considered to be not transition elements or non-transition elements. These are in fact D block elements because they fall within the definition of what D block elements are. Their highest energy electrons are getting filled into a D subshell. However, they do not contain any incompletely filled D subshells when they are producing ions or when they are present as just elements. So therefore, zinc, cadmium and mercury are not going to produce any colored solutions in aqueous medium. So zinc 2 plus, cadmium 2 plus and mercury 2 plus ions and their aqueous solutions are not going to produce any colored compounds. But if you take a look at the following D block elements like titanium 4 plus, copper 1 plus and scandium 3 plus, although these elements are considered as transition elements, these specific ions that we are considering over here does not contain any incompletely filled D subshells. So therefore, they do not produce any aqueous solutions with a color. So these aqueous solutions are going to be colorless. So titanium 4 plus aqueous solutions, copper 1 plus aqueous solutions and scandium 3 plus aqueous solutions are all going to produce colorless solutions. In this slide, we are going to look at why are aqueous cations of transition elements colorful? What is the reason for cations of transition elements to have any color? So let's go through this note here. Aqueous solutions of many transition metal ions can absorb radiation in the visible region of electromagnetic spectrum. So when aqueous ions or metal ions are present, especially when they have incompletely filled D subshells, they can absorb energy from the visible light region of the electromagnetic spectrum. This causes the ions or ion solutions to produce a color because the energy is absorbed from the visible region of the electromagnetic spectrum. So this ability is due to the presence of partially filled D subshells, as I mentioned earlier. So this is something that should be there for a transition element to produce color. It should have partially filled D subshells. So therefore, whenever you have these two configurations, D0 or D10 electronic configurations, even in transition elements, if their ions are containing D0 or D10 electronic configuration, at that point they don't have any partially filled D subshells. So therefore, they will not produce any ions or ion solutions with a color. So for example, if you take scandium, zinc 2 plus, titanium 4 plus and copper 1 plus, we saw in the previous slide as well, they do not form any aqueous ion solutions with a color. So in this slide, we are going to explore why D block elements form complexes or complex ions. So one of the most important features of D block elements is the formation of complex ions. D block elements are capable of forming coordination complexes. The reason for this is that d block elements have the ability to take in a pair of electrons from another species that is able to donate a pair of electrons. Normally, electron-rich species that ends up donating a pair of electron is referred to as a ligand. And by doing so, they form a dative bond, or else in this situation we will call them a coordinate bond. So in this situation, neutral atoms, positive or negatively charged ions can form coordinate bonds with a central metal ion or an atom. So in d block elements, since they have partially filled d orbitals, they are capable of taking in a pair of electrons when an electron-rich species or anything that is capable of donating a pair of electrons donates a pair of electrons. The 3D elements are capable of taking those electrons because they have partially filled d orbitals. So as most complexes have charges, they are often called complex ions. When there is no overall charge, the term complex is used. So you might have seen these types of complexes, and normally we call them coordination complexes. However, if there is an overall charge, we call them complex ions. For example, when nickel is forming 6 coordinate bonds with 6 water molecules, so at this point we can call them water ligands, we are forming nickel H2O6 2 plus complex ion. So we can call it a complex cation because the charge, overall charge, is 2 plus. And over here, this is a neutral complex. With the nickel atom, we can see 6 carbon monoxide molecules are forming a coordinate complex. So overall charge over here is 0. So therefore, we end up calling them a neutral complex. And then we have complex anion. Nickel 2 plus is now taking electrons or forming coordinate bonds with 6 cyanide groups. In this case, each cyanide group carries a negative charge, and nickel is a positively charged ion, or nickel 2 plus ions are positively charged ions. So you can see the overall charge of this complex ion is 4 minus, and negatively charged complexes like this are referred to as complex anions. So we had a look at complex cations and neutral complexes and complex anions. While keeping this in mind, let's move on to our next slide. Over here, in the next slide, we're actually going to see how the coordinate complexes are made. So complexes are formed due to electron-rich species donating a lone pair of electrons to the central metal atom or ion and forming coordinate bonds with it. So as I mentioned earlier, there are chemical species that can be atoms, positively charged ions or negatively charged ions, that are capable of donating a lone pair of electrons towards the central metal ion, or sometimes it's a central metal atom that you have. So the central metal ion receives these lone pairs of electrons and forms a coordinate bond with that particular chemical species. What they form is referred to as a coordinate bond. So when a few of these chemical species, which are normally referred to as ligands, are donating pairs of electrons, they form a coordinate complex. And as seen in the previous slide, if the coordinate complex or coordination complex has an overall charge, you're going to have a complex ion. If you don't have overall charge, you form a neutral complex. So the presence of partially filled 3D subshells of these elements is the main reason why they can accept incoming lone pairs of electrons. So this is a good example. For example, if you take copper 2 plus, you can see ammonia. Each of these ammonia contains a lone pair of electrons that can be donated towards forming a coordinate bond with copper 2 plus ion here. So therefore, you can see when 4 ammonia molecules are donating lone pairs like that and forming a coordination complex, the final result is this. Copper, a single copper 2 plus ion forms 4 coordinate bonds with 4 ammonia molecules and contains an overall charge of 2 plus. So this is a complex cation. So this is why the 3D elements or transition elements can form complex ions or coordination complexes. Now, the species that donate electrons, normally anything that can donate a pair of electrons are referred to as a Lewis base. So species that ends up donating electrons are going to be referred to as a Lewis base. So when it comes to nickel 2 plus ions forming a coordination complex, it forms 4 coordinate bonds with 4 ammonia molecules. So ammonia is the one that is donating a lone pair towards nickel 2 plus ion. So therefore, nickel is going to be the one that is receiving electrons and it is considered a Lewis acid. And ammonia, the one that is donating a pair of electrons, is referred to as your Lewis base. And then you can see it is forming a complex ion. So at the same time, we can see the ligand is ammonia. So the ligands that are coordinated to the central metal ion play a major role in determining the overall color of the complex. So not all nickel 2 plus ions are going to have the same color as this complex. Nickel 2 plus aqueous ions and nickel 2 plus ions, when connected to 4 ammonia ligands, are going to have 2 different colors, and we are going to be observing these colors today. So keep in mind the ligands that is connected to a central metal ion determine the color of that specific complex. So a complex's color varies based on the ligands that are attached to it. Now, let's move on to our experiment. So in our experiment, we are going to first look into copper 2 plus ions. So after this theory part, you will observe the actual experiment in the lab environment. So before you move on to our lab experiment, we have to have the necessary theory knowledge. So let's move on to copper 2 plus and related experiments and see what type of reactions are taking place here. So we have copper 2 plus ion solution. So normally in the lab environment, we obtain the copper 2 plus ions through our copper sulfate. So we have copper sulfate is an abundant chemical in the lab. So we go to the lab, we have copper sulfate. It is normally present in the hydrated form. So you take copper sulfate 5H2O and you dissolve it in a little bit of water. So copper sulfate 5H2O, in the solid form is a blue color solid. It's a pale blue color crystalline solid. So as you can see over here, if you take it to a weighing boat, or if you take it to a watch glass, it's going to appear a blue color crystalline solid. If you dissolve it in water, it produces a pale blue color aqueous solution. So the pale blue color of this solution is due to the formation of a complex ion. So copper 2 plus ions present in copper sulfate is going to form a complex ion by forming 6 coordinate bonds with 6 water molecules, and they form copper 6H2O 2 plus complex ion. And the color of this complex ion is going to be pale blue in color. Or in other words, we can say aqueous copper 2 plus ions have a pale blue color. So this is the first observation that we are going to make when you are dissolving copper sulfate in water. And then we are going to move on to the next step, formation of a complex ion by adding concentrated hydrochloric acid to our aqueous copper sulfate solution. So we have copper 2 plus ions obtained from dissolving copper sulfate. So now we have copper 2 plus ions in the aqueous medium, and to that we are adding concentrated hydrochloric acid. So students, at this point what we are going to do is we are increasing the chloride ion concentration in the medium by adding concentrated hydrochloric acid. So due to the increase of chloride ion concentration in the medium, water ligands will be replaced by chloride ligands. So if you remember correctly, earlier I told you that a color of a complex depends on the ligands that are attached to it. So copper 2 plus ions, when it is connected to 6 water ligands, appeared pale blue in color. However, when copper is connected to 4 chloride ligands, the color is going to be yellow. So we can very clearly see this observation, but you will sometimes, when you are carrying out this experiment, you will see the pale blue color solution initially turns a green color, and then it turns a yellow color. Alright, so you have all of the water ligands replaced by chloride ligands, forming copper or CuCl4 2 minus complex ion, which is going to be a yellow color complex ion. So this reaction is reversible, meaning if you add more and more chloride ions, the pale blue color solution will turn into a yellow color copper chloride complex. However, if you add water to a yellow color solution where you have CuCl4 2 minus ion, it will actually revert back into our pale blue color aqueous copper ion solution, forming a CuH2O6 2 plus complex ion. Right, so now let's move on to the next part of this experiment. Actually, this is a basic explanation to what I just told earlier. When you are adding concentrated hydrochloric acid in an intermediary stage, you are going to observe the formation of a green color solution. This is only there for a short period of time, and then it converts to a yellow color solution. So eventually the solution, pale blue color solution, turns to a yellow color solution. So the species that cause this green color is given here. When out of the 6 water ligands connected to copper, when a few of those water ligands are replaced by chlorine or chloride ions, we can see the green color complex being formed. So when you have copper, 1Cl and 5H2O plus complex, so basically you can see one of the water molecules. There are 6 water molecules here, and over here one of the water molecules is replaced by a chloride ion. CuCl 5H2O plus complex ion is going to be the reason for the formation of this green color solution. And then this is just an intermediary phase, because this is going to further react with the chloride ions in the medium, and all of the water molecules are going to be replaced by chloride ions, and we are going to eventually form CuCl4 2- complex, which is going to be yellow in color. Right, so please keep this in mind, because this is a very important observation. So eventually what you form is CuCl4 2-. As I mentioned earlier, students, we have copper sulfate in the lab in the hydrated form. So in the hydrated form, you have 5 water molecules always connected to the copper sulfate. So when you take the hydrated copper sulfate salt, it is going to appear blue in color. So the solid copper sulfate or hydrated copper sulfate solid is going to be blue in color. One of the aims of this experiment is to observe that the hydrated salts sometimes happens to be colored. So we can see it over here. The hydrated copper sulfate has a color which is blue. However, if you take this hydrated solid or copper sulfate solid and heat it to remove the water, you would observe that it turns into anhydrous copper sulfate, meaning there's no water now attached to the solid copper sulfate. So anhydrous copper sulfate is going to appear white in color. So anhydrous copper sulfate can be obtained by heating the hydrated copper sulfate solid that we have. So if you heat it long enough, you would see the pale blue color of the copper sulfate is disappearing to form a white color solid, and 5 water molecules will be removed in this process. Why is this important? Because at this point you can understand, if you want to identify the presence of water, you can actually use anhydrous copper sulfate. So anhydrous copper sulfate, if it comes into contact with water, what will happen? It will reform the hydrated form of the copper sulfate solid, and the hydrated solid is going to be pale blue in color. So for example, if you are carrying out a reaction and you have a vapor produced and you want to figure out whether the vapor produced is in fact water, what you can do is you can send, or we can make that vapor come into contact with anhydrous copper sulfate. And if that vapor converts anhydrous copper sulfate, which is white in color, to a blue color solid, that means that vapor was in fact water. Because when anhydrous copper sulfate comes into contact with water or water vapor, or even in atmospheric vapor is actually enough, if you let it react with anhydrous copper sulfate for long enough, it will convert anhydrous copper sulfate into the hydrated form, which is pale blue in color. Alright, so this is a test that can be done to identify water. Let's move on to our next slide. Now in this slide, we are going to be looking at adding ammonia or ammonium hydroxide to a dilute solution of copper 2+ ions. So we have a copper 2+ ion solution, again obtained through dissolving copper sulfate. and we are going to add dilute ammonia or ammonium hydroxide. So ammonium hydroxide is going to introduce hydroxide ions into the medium. So to introduce hydroxide ions into the medium, we can also use a dilute solution of sodium hydroxide. We will obtain the same result. So in the presence of hydroxide ions, copper 2 plus ions will react with hydroxide ions to form copper hydroxide, CuOH2, which is a water insoluble solid. So this coordination complex can also be indicated as CuOH twice and H2O4 solid. So it doesn't have a charge because you can see the hydroxide ions, two negative charges, or actually each hydroxide ion brings in one negative charge. Since there are two hydroxide ions, it is going to neutralize the two positive charges found on the copper 2 plus ion. And it is going to form a water insoluble precipitate, which is going to be a pale blue color precipitate. So upon addition of dilute ammonia or upon addition of dilute sodium hydroxide or any species that can actually release hydroxide ions, they are going to react with the copper 2 plus ions and form copper hydroxide, which is going to be a pale blue color precipitate. This is going to be a pale blue color precipitate. So this same reaction can be written the following way as well. Instead of writing like this, we can just write the copper hydroxide solid. Instead of writing its complex or coordination complex formula, you can just write copper hydroxide or CuOH twice solid as well. So that equation is this. So both forms of this equation are correct, and the final result is going to be just the formation of water insoluble blue color precipitate being formed. And then we have the second step. So after forming this blue color precipitate, what happens? Or if you take excess amount of ammonia, so they say upon addition of further ammonia, the pale blue color precipitate will dissolve and a dark blue color solution will be formed. So imagine over here, if you have a pale blue color precipitate, right? So you have a pale blue color precipitate here, and this pale blue color precipitate will dissolve in the presence of excess ammonia, or if you add concentrated ammonia, and will form a dark blue color solution. So this is happening because the copper 2 plus ions are capable of forming a complex ion with 4 ammonia ligands. So when the ammonia concentration is quite high in the medium, at that point the OH minus ligands will be going away and those ligands will be replaced by ammonia ligands and will form a dark blue color copper ammonia complex. So copper and 4 ammonia ligands together will form CuNH3 4 times with a 2 plus charge. They are forming a complex cation which is blue in color. So at the same time, we can directly get to this dark blue color copper ammonia complex by taking a copper 2 plus ion solution and directly reacting it with a higher concentration of ammonia or concentrated ammonia solution. So when we directly react copper 2 plus ion solution with excess of ammonia molecules, it bypasses the formation of copper hydroxide, which is a pale blue color precipitate, and directly forms a dark blue color solution. So keep in mind, students, if you take dilute ammonia, it is going to turn copper 2 plus ions first into copper hydroxide, which is a pale blue color precipitate, and upon addition of further ammonia, it will turn into a dark blue color solution due to the formation of copper ammonia complex. Copper forms a complex ion with 4 ammonia ligands. Or if you take copper 2 plus ion solution and directly react it with highly concentrated ammonia solution, then what happens is copper 2 plus then at that point directly forms a copper ammonia complex, which is dark blue in color. So that is what you observe over here. Now you have to keep in mind that we can form copper hydroxide with sodium hydroxide as well. But is that an observation when you add excess amount of sodium hydroxide? The answer to that would be no. If you take the copper hydroxide solid, which can also be formed by reacting copper 2 plus ion solution with sodium hydroxide, because sodium hydroxide will also introduce hydroxide ions, you will form this copper hydroxide solid. So after the copper hydroxide is formed, if you add excess amount of sodium hydroxide, you do not observe any change, because copper 2 plus ions do not form a complex ion or coordination complex with sodium. So therefore, you will not see this copper hydroxide solid dissolving in excess sodium hydroxide. So you have to keep in mind, with ammonia, if you add just a little bit of dilute ammonia, copper will form copper hydroxide, and then in presence of excess ammonia, it is going to dissolve to form a dark blue color solution. So you can say the precipitate that is formed is going to dissolve in excess ammonia. However, this is not observed in sodium hydroxide. In sodium hydroxide, when you add a little bit of sodium hydroxide to copper 2 plus solution, it will form the same copper hydroxide precipitate that we observed when we added ammonia. However, in excess sodium hydroxide, this precipitate will not dissolve. So that is an important observation to keep in mind. And now we are moving on to a good test that we can use for identification of copper hydroxide. So you have copper hydroxide precipitate obtained through reacting copper 2 plus ions with hydroxide ions. And then if you take that precipitate, copper hydroxide precipitate, and heat it, you would see when you are heating the copper hydroxide pale blue color precipitate, it will convert into a black color precipitate. This black color precipitate or black color solid that is formed over here is going to be our copper oxide solid. So upon heating copper hydroxide, which is pale blue in color, it turns to a black color copper oxide. So that is also an important observation to keep in mind. This is very easy to conduct as well. You take a little bit of the precipitate that you have obtained through reacting a hydroxide ion solution with copper 2 plus ion solution. You remove the precipitate from the mixture, you take it to a boiling tube, and you heat it for a while, and you will observe the pale blue color precipitate turns into a black color solid due to the formation of copper oxide. And the equation for that is given here. Now, let's move on to our next experiment. So this is one of the most interesting experiments you can do with copper 2 plus ions. So copper 2 plus ions, when it is reacted with potassium iodide, when copper 2 plus ions are reacted with potassium iodide, the copper 2 plus can oxidize the iodide ions and turn iodide into iodine, while the copper 2 plus will reduce to copper 1 plus, forming Cu2I2, which is going to be a white color precipitate. So this reaction is an interesting reaction because you form a mixture, or you form a mixture of a precipitate which is white in color, and the supernatant is going to be a brown color. So as you can see in this reaction, copper 2 plus ions are there in the initial solution as one of the reactants, and then you have iodide ions again as one of the reactants, and you can see the copper 2 plus ions are going to be obviously pale blue in color. In aqueous medium, copper 2 plus is pale blue. What about iodide ions? Iodide ions does not have a color. However, a solution of iodine is going to be brown. So the reactant iodide does not have a color. But as the reaction proceeds, what happens? The copper 2 plus gets reduced to copper 1 plus and forms Cu2I2, which is a water insoluble white color solid. And the iodide ions get oxidized. Iodide has oxidation state of -1, and it get oxidized into I2, iodine, which has oxidation state of 0. So -1 to 0 is oxidation. So copper 2 plus ions are acting as an oxidizing agent at this point. And this will result in forming a white color solid along with a brown color aqueous solution. So it is going to appear like this. You can see over here we have a white color, precipitate and a brown color solution. A white color precipitate and a brown color solution. So everyone, you have to keep in mind when you're conducting this experiment, due to the brown color of the solution, even the precipitate might appear brown. So if you're not closely observing the color of the precipitate, you might be deceived into believing even the precipitate is brown in color. But upon close observation, you might notice that the precipitate is in fact white. So the white color precipitate is Cu2I2, cuprous iodide. So although this is a very important part again, so this statement is just what I mentioned earlier. So keep in mind, although the precipitate is white, it might appear brown, but upon close observation you will notice that it is in fact white. So you have to remember this equation and this experiment. You can actually use this experiment to identify the presence of copper 2 plus ions. And actually you can use this experiment. In this part of our experiment, we are going to be observing the white color of the precipitate that we formed earlier very clearly. So how can we do that? We can actually do that by removing this brown color solution. So we saw earlier the cuprous iodide precipitate was not very clearly observed due to the presence of iodine in aqueous medium, because iodine is going to appear brown. So if you remove the iodine by reacting it with sodium thiosulfate, we are going to have a colorless solution, because when Na2H2O3 reacted with iodine, it's going to turn into sodium tetrathionate, which is also going to be colorless, as well as iodine is going to convert into iodide ions, which does not have a color. So we are going to turn this brown color solution into a colorless solution. So at this point, students, we are going to be forming, you will see the white color precipitate remaining at the bottom, which is Cu2I2, and at the same time you will observe that there was a precipitate, white color precipitate over here, but it is not going to be very clear to you initially. However, after the reaction of after the reaction that takes place between iodine and sodium thiosulfate, the solution will turn colorless, indicating the presence of, or very clearly allowing you to observe the presence of, a white color Cu2I2 precipitate. So what you see over here would be the presence of iodide ions, which is going to be colorless, and the white color precipitate that you see over here is going to be Cu2I2 solid, which is white in color. So this can also be used for a titration to calculate the concentration of copper 2+ ions. And then, students, on additional note, we can actually focus our attention on identifying the presence of iodine. So as you know, iodine is used to identify the presence of starch. So if you take a little bit of starch and add, or starch solution, and add it to a solution containing iodine, what happens is, due to a formation of a complex, it is going to form a blue-black color. The entire solution will turn to a blue-black color, depending on the concentration of the iodine, depending on how much starch is present. Sometimes the color might vary. If the iodine concentration is quite low, it will be a lighter blue color. But most of the times, when you are adding starch to iodine or iodine to starch, what you're going to observe is a really dark blue-black color, more towards black, right? So you're going to see a blue-black complex being formed, and therefore the solution will appear blue-black color. Right, students, so keeping that in mind, let's move on to our next experiment. So initially, we looked at copper 2+ ions and their reactions with HCl, ammonia, and then we further moved on to its reaction with potassium iodide. Now, we are going to start with nickel. Identification test for nickel 2+ ions. So, normally, if you take nickel in the lab, most of the time we can obtain nickel salts in the hydrated form. So nickel chloride 6H2O solid is going to appear green, a green color solid. So when you take our nickel chloride hydrated solid, which is green in color, and if you dissolve it in water, what you're going to observe is the formation of a green color solution. So the solid was green, and the solution that is formed when dissolved in water was also green. And we observe the same situation when it comes to copper 2+ as well, right? So we saw the copper sulfate, the hydrated salt, was blue in color, or pale blue in color. When dissolved in water, the solution that was formed was also pale blue in color. This green color solution is there due to the formation of complex between nickel 2+ and 6 water ligands. So we have over here our nickel 2 plus, and when it forms a complex with 6 water ligands, we form NiH2O6 2 plus complex ion, which is going to be green in color. In this part of our experiment, what we're trying to do is we're trying to react the nickel 2 plus ions with hydroxide ions. For this purpose, we can add sodium hydroxide. We can add sodium hydroxide to our nickel 2 plus ion solution. Now we know the nickel 2 plus ion solution is going to be green in color due to this complex that is out there. And then when it comes into contact with hydroxide ions, nickel will form a water insoluble precipitate, which is nickel hydroxide, NiOH twice, or Ni connects with 2 hydroxide ions to form a water insoluble precipitate, which is green in color. And you can see that over here as well. Very clearly, we can see the formation of a green color precipitate. So the green coloration of the solution will disappear because the green coloration of the solution was there due to the presence of nickel 2 plus ion complex. So that complex will now not be there due to the formation of nickel hydroxide. So the nickel ions used in forming this complex with water molecules will be used to form nickel hydroxide. Therefore, the green coloration of the solution will no longer be observed, but the solution will now start producing a precipitate which is green in color. Now, in an additional step, if you add excess sodium hydroxide, like we have done over here, if you add excess sodium hydroxide, you are not going to be observing any color change. This is because the precipitate is not going to dissolve in the presence of excess sodium hydroxide. Now, can you remember when it comes to copper, when reacted with sodium hydroxide formed copper hydroxide, which was a pale blue precipitate. This also followed the same trend. The copper hydroxide did not dissolve in excess sodium hydroxide. Similarly, nickel hydroxide, which is a green color precipitate, does not dissolve in excess sodium hydroxide. However, we are going to now observe a similar reaction instead of the use of sodium hydroxide. In this step, we are going to be using dilute ammonia or ammonium hydroxide. So if you take a nickel 2 plus ion solution and react it with ammonium hydroxide does the same thing as sodium hydroxide did earlier in the previous step, which is the introduction of hydroxide ions into the medium. So the hydroxide ions will come into contact with the nickel 2 plus ions in the medium and will form our nickel hydroxide solid, which is a water insoluble solid. So therefore, you can observe the formation of our green color precipitate. So this step we are familiar with through the previous slide. So we can use ammonium hydroxide or sodium hydroxide or any other hydroxide releasing solution to produce this green color precipitate. But the next step is going to be the interesting step. What happens if you react this precipitate that is formed with excess ammonia, or when you add concentrated ammonium hydroxide? What happens to the precipitate? So let's say you have a precipitate over here. Now the green color is actually a green color precipitate, so therefore you will have our green color precipitate over here. So the green color precipitate is going to dissolve to form a blue color solution. So students, this was not observed in sodium hydroxide. When you take nickel hydroxide and react it with excess of sodium hydroxide, there was no reaction. However, if you take our nickel hydroxide precipitate and if you react it with excess ammonia, it is going to form a dark blue color or deep blue color solution. So this solution is there due to the formation of a complex between nickel 2 plus ions and ammonia molecules. So 6 ammonia molecules are going to form a coordination complex with nickel 2 plus, forming nickel 6 ammonia and 2 plus complex. So this is going to be a deep blue color or a dark blue color solution. So it's very important to keep in mind, nickel hydroxide does not dissolve in excess sodium hydroxide, but it does dissolve in excess ammonia, and it forms a dark blue color solution. Now a similar observation was made when it comes to copper as well. If you take copper hydroxide is pale blue in color, which is a solid precipitate, did not dissolve in sodium hydroxide, but it did dissolve in excess ammonia to form a dark blue color solution. So copper forms a complex with ammonia ligands, which is dark blue color, and so does nickel. So this equation or this reaction can be observed when you directly react nickel 2 plus ions without the formation of nickel hydroxide, right? If you directly take a solution of nickel 2 plus and react it with excess ammonia or excess concentrated ammonium hydroxide, you are going to see the formation of nickel ammonia complex. So nickel ammonia complex is going to be again dark blue in color, and you do not see the formation of nickel hydroxide. So it bypasses the formation of nickel hydroxide if you directly react the nickel 2 plus ions with excess ammonia or concentrated ammonia straight away. Now, in this part of our experiment, we are going to use a different reagent. Now, we use the bases sodium hydroxide and ammonia. Now, we are going to be using hydrochloric acid. So, this hydrochloric acid we are going to be using over here is concentrated, because the purpose of this is to introduce a higher concentration of chloride ions into the medium. So, when you react nickel 2 plus ions with concentrated HCl, it is going to start replacing the water ligands in the nickel water complex and form NiCl4 2 minus complex ion. So this is due to all of the water molecules being replaced by chloride ligands. So the 6 water ligands that we see over here are now replaced by these 4 chloride ligands. So now we have formed nickel chloride complex, or complex between nickel 2 plus ions and chloride ions. So this complex is yellow in color. As I mentioned earlier as well, depending on the ligands that are connected to a metal ion, the color of the complex formed is going to vary. We can see when nickel is connected to 6 water molecules, it is forming a green color complex, and when nickel is connected to 4 chloride ligands, it is forming a yellow color complex. So this is a observation to be made when you're carrying out this reaction. So this will give us an idea of what this ion is. If a green color ion turns to a yellow color upon the addition of concentrated hydrochloric acid, you can see it could be nickel 2 plus ions that are present in the medium. Now we move on to our next metal ion, which is cobalt 2+. Now cobalt 2+ ions in the lab can be obtained by a cobalt salt. So we have taken cobalt chloride salt again. We have the hydrated cobalt chloride. So if you take cobalt chloride 6H2O, it is going to be pink in color. And the pink color solid, when dissolved in water, forms a pink color solution. Same trend continues. Pale blue color solid forms a pale blue color solution. Green color solid forms a green color solution. And this is the previous two instances we looked at today. And when it comes to the pink color solid, when dissolved in water, formed a pink color solution. So the solution is pink due to cobalt 2+ ions forming a complex with 6 water ligands, COH2O6 2+. So this complex ion has a pink color. Now, while keeping this information in mind, let's move on to our next reaction. So we have cobalt 2+ ion solution, and we are going to be reacting this ion solution with sodium hydroxide. So when reacted with sodium hydroxide, like in the previous two instances, what we are trying to obtain here is OH- ions or hydroxide ions. So when hydroxide ions comes into contact with cobalt 6H2O complex, it is forming this complex. One cobalt 2+ ion is now forming coordinate bonds with 1 hydroxide ions and 5 H2O molecules. So this coordinate complex, which has an overall positive charge, is going to be blue in color. So this complex is a blue color complex. So now students, while observing this blue color complex, you have to keep in mind that unlike the hydroxides that were formed in the previous two instances, when it comes to cobalt, what you're going to be observing is something different. We saw when it comes to nickel, when reacted with hydroxide ions, it formed a pale blue color precipitate. So the solution was pale blue, and when reacted with hydroxide ions, the precipitate formed was also pale blue. When it comes to nickel, the solution was green, and when reacted with hydroxide, it formed a green color precipitate, which is nickel hydroxide, but not with cobalt. So cobalt solution, when reacted with hydroxide ions, first forms a blue color precipitate due to formation of a complex between 1 cobalt 2+ ion, 1 hydroxide ion, and 5 water ligands. So when excess aqueous ammonia or concentrated ammonia is added to the precipitate dissolves to form a yellow-brown solution. So just like in the previous two instances also, this time we can see the precipitate dissolves in the presence of excess ammonia. So although the color of the precipitate does not necessarily resemble the color of the solution, we can see there's one characteristic still remains, that is, in the presence of excess ammonia, the initially formed precipitate dissolves. So you can see if you take the blue color precipitate, now we have color this entirely blue just to kind of give you an idea or remind you the color of the precipitate, which is blue. And then we can see the blue color precipitate, the solid, actually reacts with excess ammonia to form a yellow-brown color solution. So this solution that you have is yellow-brown due to cobalt forming a complex with ammonia ligands. So 6 ammonia ligands comes into contact with one cobalt 2 plus ion and forms a coordinate complex, which is going to be yellow brown in color. So you can actually use this to identify the presence of cobalt 2 plus ions. And then we move on to another reaction where you can see when a solution of cobalt 2 plus ions are reacted with concentrated ammonia directly, first reacting it with dilute ammonia. If you directly react it with concentrated ammonia, you will not see the formation of the blue color precipitate. You can see the pink color solution directly turning into a yellow-brown aqueous solution. So this is due to directly replacing all of the water ligands with ammonia ligands and forming cobalt ammonia complex ion, which is going to be a yellow-brown in color. So students, this is how cobalt 2 plus ions react with hydroxide ions, and this is how cobalt 2 plus reacts with ammonia. And now we are moving on to another aspect of the same reaction. So if you take the yellow-brown solution that we have formed, right? So we have formed a yellow-brown solution by reacting cobalt 2 plus with excess of ammonia, and this cobalt ammonia complex can get oxidized. The cobalt 2 plus actually, or cobalt as an element has two stable oxidation states, 2 plus or 3 plus. So cobalt 2 plus over here present in this particular complex can get oxidized to form cobalt 3 plus. So the cobalt over here in the second complex to our right hand side is having an oxidation state of 3 plus. So this oxidation can happen when reacted with an oxidizing agent such as hydrogen peroxide. So if you take hydrogen peroxide and if you react the cobalt ammonia complex with hydrogen peroxide, you will see that yellow-brown solution turning into a red-brown solution. So the reason for the color change is because the cation now has changed in its oxidation state. Cobalt 2 plus has now changed to cobalt 3 plus. So it forms a red-brown color solution, as you can see over here. So over here, the main observation to know or keep in mind is the charge of the complex that is formed is turning from +2 to +3. And students, this oxidation can happen with atmospheric oxygen as well. Atmospheric oxygen also can convert cobalt 2 plus into cobalt 3 plus. However, this oxidation will happen very slowly. Hydrogen peroxide is a good oxidizing agent, so as soon as you react this complex with hydrogen peroxide, the reaction will happen quite fast, turning cobalt 2 plus and cobalt 3 plus. But if you are trying to convert cobalt 2 plus to cobalt 3 plus with the use of atmospheric oxygen, it will take a long time. However, at the end, you can obtain a red-brown solution, but the reaction is going to be having a slower rate. So what I just mentioned is present here as well. So compared to hydrogen peroxide, the reaction rate will be much slower. That is one point to keep in mind. This reaction can be facilitated via atmospheric oxygen, but the rate of the reaction is much slower. So in this part of our experiment, we are going to take our cobalt chloride 6H2O hydrated solid, and we are going to add it to ethanol. So ethanol is going to remove the water molecules from the solid and form cobalt chloride 2 minus or COCl4 2 minus complex, which is going to be a blue color complex. So upon addition of ethanol, or if you take our cobalt chloride solid and if you react it with ethanol, we are going to produce cobalt chloride complex ion, which is going to be blue in color. So COCl4 2 minus complex ion is going to be blue in color. This can be obtained by removal of water from our hydrated cobalt chloride solid. So the removal of water was done previously with the addition of ethanol. In this part of the reaction, what we are going to do is we are going to take a cobalt 2 plus aqueous ion solution, which is going to be pink in color, because we know when 6 water ligands is connected to cobalt 2 plus, it forms a complex that is going to be pink in color, cobalt 6H2O2 plus. So this complex is present in aqueous cobalt 2 plus solution, and what we are going to do is we are going to take a filter paper and we are going to dip it in the solution, and we are going to allow the filter paper to absorb the solution, and it will turn pink as the solution gets absorbed into the filter paper. So the filter paper, after we take it out, will remain pink. So then what happens is we are going to take this pink color filter paper and we are going to heat it up. So the heating this filter paper is going to remove the water molecules that are present in this compound or in this complex. So due to the removal of the water, we are going to form COCl4 2 minus complex ion. We saw earlier in the previous slide, COCl4 2 minus is going to be a blue color complex. So this cobalt soaked filter paper turns blue in color if you heat the paper to remove the water from it. So as the water gets removed, the color turns to blue. So this is a reversible reaction. So therefore, if you take that blue color filter paper and now if you hold it against a water vapor, or if you let it react with the atmospheric water vapor that we have around us, little by little you will see this blue color filter paper now is starting to turn into a pink color again. So we can actually use this type of filter paper to identify the presence of water. So we actually do use them. We call this cobalt paper. So cobalt paper is normally going to be pink in color when there is water present. If water is removed from that cobalt paper, it is going to appear blue in color. Due to the removal of water, you are going to be forming COCl4 2 minus complex ion, which is going to be blue in color. Since this is reversible, upon addition of water to the blue color cobalt paper, it is going to turn into a pink color again due to forming a complex ion with 6 water ligands. Cobalt 2 plus forms a complex ion with 6 water ligands, which is pink in color. So you can use this to identify the presence of water. So what happens if you take our cobalt 2 plus aqueous ion solution and react it with concentrated hydrochloric acid? So we have the usual cobalt 2 plus aqueous ion solution, and then we are bringing in concentrated hydrochloric acid. and reacting with cobalt 2 plus ions. At this point, this pink color complex is going to come into contact with a lot of chloride ions through HCl. So then what happens? The chloride ions will start replacing these water ligands with chloride ions and will form again cobalt. One cobalt 2 plus ion will come into contact with 4 chloride ligands and will form COCl4 2 plus complex, which is blue in color, and the 6 water ligands will be removed from the complex. So this reaction, of course, like I mentioned earlier, is reversible. If you have enough and more chloride ions in the medium, the equilibrium will be shifting to the right hand side, producing the blue color cobalt and chloride ion complex. And if you dilute the medium by adding more and more water, this blue color solution will start turning into a pink color. So as you can see, this is a reversible reaction. If you add more chloride ions, it will turn to a blue color solution. If you add more water, it will turn to a pink color solution. Now students, we have come to an end of the theory parts revolving around experiment number 21. So in this experiment, we looked at copper 2 plus, nickel 2 plus, and cobalt 2 plus. For obtaining copper 2 plus ion solutions, we used copper sulfate, the hydrated salt of copper sulfate, which was a pale blue color solid, and when dissolving it in water, we produced a pale blue color solution. When it comes to nickel, we used nickel chloride hydrated solid, which was green in color, and when dissolved in water, that formed a green color solution. And when it comes to cobalt, we used cobalt chloride hydrated solid. When dissolved in water, that produced a pink color solution, and the hydrated solid itself was pink in color. So we saw the solids were the same color as the solutions. And then we added hydroxide ions to each of these ion solutions. Copper 2 plus, when reacted with hydroxide ions, produced copper hydroxide, which was pale blue color precipitate. It did not dissolve in higher concentration of sodium hydroxide. However, copper hydroxide solid dissolves in ammonia, excess ammonia. So if you add excess ammonia, it is going to dissolve to form a dark blue color solution, because copper forms a complex with ammonia. And then we took nickel. Nickel, when reacted with hydroxide, produced nickel hydroxide, a green color precipitate. It also did not dissolve in excess sodium hydroxide. However, in excess ammonia, it dissolved to form a deep blue color solution again. So this was due to nickel forming a complex with ammonia. And when you take cobalt, when reacted with hydroxide, it did not form a pink color solid. It formed a blue color solid, which is insoluble in water. So this blue color precipitate, when reacted with excess sodium hydroxide, did not produce any different outcome. However, when it was reacted with excess ammonia, it formed a yellow-brown solution. So these were some of the main observations, and then we moved on to reacting all of these with HCl. So you have to keep in mind the colors of each of these compounds, and whenever we conduct a specific experiment, what the outcome of it was, you have to keep in mind when going into the lab to conduct these experiments. Otherwise, when you are conducting this experiment, you would not make out what is actually going on. So without further ado, let's move on to the laboratory and actually conduct this experiment. Students, Today I will be looking at GC Advanced Level Chemistry Practical 21. In this practical, we will be focusing on observing the color changes of copper 2 plus, nickel 2 plus and cobalt 2 plus when it is treated with dilute ammonia, concentrated ammonia and concentrated hydrochloric acid. So for this experiment, let's take a look at the reagents we need. Students, now we will take a look at the reagents and other materials we need to start this practical. We have here a cobalt nitrate. It's a pale red color solid. Over here is nickel nitrate. Again, we have here solid crystals which are green in color. And we have here copper sulfate, a blue color solid. Apart from that, we will be using concentrated hydrochloric acid, dilute ammonia, concentrated ammonia and hydrogen peroxide. Other materials that we will be using is boiling tubes and a wash bottle containing distilled water. Let's move on to the practical now. Students, now let's start our practical. We'll first take a boiling tube and we'll add some solid copper sulfate into this boiling tube and we'll dissolve it with some distilled water. Here you can see I'm using a spatula to take a small amount of copper sulfate and I'm placing it in the boiling tube. Now I'll be taking a wash bottle. This is filled with distilled water. So I'll be adding distilled water into this boiling tube to dissolve the solid copper sulfate. As you can see, when I added water into this boiling tube, we are forming copper sulfate aqueous solution which is blue in color. Let's compare it against a white color background for us to see the color change clearly. It's a pale blue color solution. This solution, here we have, with every copper 2 plus ion, there are 6 water ligands forming coordinate bonds here. So we name it hexa aqua copper 2 ions. So this is the color of the hexa aqua copper 2 ion complex. Let's move on and treat this with dilute ammonia, concentrated ammonia and hydrochloric acid. Before we do that, let's start with adding a little bit more water because we'll be needing a little bit more solution than this. So we'll add a little bit more water. Now let's transfer some of this copper sulfate solution into another boiling tube. So to this other boiling tube that we took, we are planning on adding a little bit of dilute ammonia. Upon addition of dilute ammonia, we are expecting to see a precipitate being formed, copper hydroxide. Copper hydroxide is a pale blue color precipitate. Let's see if we can get to that observation. Here I take dilute ammonia and I'm transferring a little bit of it into this boiling tube. As you can see, upon addition of even a little bit of dilute ammonia, you can see the formation of a small precipitate. Before I shake it, you can very clearly see the formation of a precipitate. So we are forming a very fine precipitate here. Because of that, it is suspended in water. for us to see the color change a bit more clearly, we will use a white color background. Over here, you will see the formation of a pale blue color precipitate, which is copper hydroxide, CuOH twice. Let me shake it a little bit so that you can see the proper pale blue color suspension over here. So this is not a solution, students. Just because it appears so, it is not a solution. It is a suspension made with the fine copper hydroxide solid particles being suspended in water. Now, let's take a little bit of this copper hydroxide suspension and treat it with a little bit of concentrated ammonia and see what happens. Before we do that, I would like to add a little bit of water to increase the amount of suspension we have. Now let's transfer some of this copper hydroxide suspension onto another boiling tube like so. To this copper hydroxide suspension, we will be adding concentrated ammonia solution. When you add concentrated ammonia into this test tube, we are expecting to see a deep blue color solution forming. Let's see if we can get to that observation. So here we have our concentrated ammonia. We'll take a little bit of it and add it to this copper hydroxide suspension. Over here you can see when you are adding concentrated ammonia, as soon as you add concentrated ammonia, you can see the deep blue color solution forming. So this deep blue color is present on top of the solution where the precipitate is still dissolving. So over here we have on the top layer the copper ammonia complex formed, and we have the copper hydroxide solid still not properly dissolved over here because I have not shaken it. So let me shake it. You can see the entire precipitate dissolves and forms a deep blue color solution with copper 2+ ions and 4 ammonia ligands. So the formula of this complex ion is CuNH3 4 times 2+. In other words, we will call this tetraamine copper 2+ ion complex. So that is the color of that complex, a deep blue color solution. Now we are going to move on to adding a little bit of copper sulfate solution into another boiling tube, because we are going to be adding concentrated hydrochloric acid into this. So we'll take a little bit more of copper sulfate solution over here. So in this copper sulfate solution, we are having copper 2+ ions, and now we will add concentrated hydrochloric acid into this copper 2+ ion solution. Upon addition of HCl, concentrated HCl, we are expecting to see a yellow color solution formed. Let's see if we can get there. When you're handling concentrated hydrochloric acid, you have to be extremely careful. As you can see, concentrated hydrochloric acid is fuming and it's actually very corrosive. So if you get it on your skin, it will cause skin damage. We will very carefully add a little bit of concentrated hydrochloric acid into this. As you can see, the first observation here is a green color. This is not at the end point yet. We will keep on adding concentrated hydrochloric acid, and I will explain why we saw a green color before it turned yellow. So to obtain our proper color change, I will have to take, because this solution is a little bit more concentrated, we'll take a little bit of this solution onto a different boiling tube, and then we will treat it again with hydrochloric acid until we reach the color that we want to observe. So let me transfer this into a different boiling tube. I have transferred a little bit of the previous concentrated solution onto this boiling tube. Now, I'll be adding a little bit of concentrated hydrochloric acid onto this until we observe the yellow color of the copper tetrachlorocopper 2- complex. Students, here you observe the yellow color of CuCl4 2- complex, tetrachlorocuprate 2 ion. This complex is going to be yellow in color. So again, to see a more clearer color change, we will compare it against the white color background. Let's take a look at what we did in short. Firstly, we took copper sulfate solid and we dissolved it in a little bit of water, and we formed a copper sulfate aqueous solution, which is pale blue in color. In this solution, we have copper 2+ ions forming a complex with 6 water ligands. And then we took a little bit of the copper sulfate solution we formed and reacted it with dilute ammonia. Dilute ammonia converted copper 2+ ions into copper hydroxide precipitate. As you can see, it has been a while since I have given it a shake, so you can see a pale blue color precipitate accumulated at the bottom. So this is CuOH twice, or in other words, copper hydroxide, which is pale blue in color. Then we transferred some of the copper hydroxide into a different test tube, and we treated that with concentrated ammonia. Upon addition of concentrated ammonia, all of the copper hydroxide solid that we had here dissolved to form a blue, actually a deep blue color solution. This is due to copper 2+ ions forming a complex with ammonia, actually 4 ammonia ligands forming CuNH3 4 times 2+ ion. Then, to a separate boiling tube, we took a little bit of our copper sulfate solution, treated it with concentrated hydrochloric acid. The copper sulfate solution we used was concentrated. So therefore, upon addition of concentrated hydrochloric acid, we did not initially see the color change we were expecting. The color change we were expecting was to see a yellow color complex being formed, which is tetrachlorocopper cuprate 2-. So that complex is yellow in color, and we have copper sulfate or copper 2+ ion complexes, which is blue in color. When those two mixed, while the transitioning state was happening, we observed a pale green color solution. This was not our end observation. Our end observation was seeing this yellow color where 1 copper 2 plus ion forms a complex with 4 chloride ions, CuCl4 2 minus ion complex. Those are the observations for copper 2 plus ion complexes. Now we will move on to nickel. Let's take a look at the complexes that nickel 2 plus ions form and their colors. In order to do that, let's transfer some nickel nitrate crystals into a boiling tube, and we will now add some water to dissolve it. As you can see, when you add a little bit of water into the nickel nitrate crystals and dissolve it, we are forming a green color solution. I will clearly show you the color after dissolving all of the solid that is still remaining here. Let's take a look at the color of nickel 2 plus ion complex with water. Here you can see a green color solution formed with 1 nickel ion. We are forming a nickel complex with 6 water ligands. So this is a hexa aqua nickel 2 ion complex, which is green in color. We move on to adding ammonia. We are starting with dilute ammonia, then we are moving on to concentrated ammonia, and finally we'll be adding a little bit of concentrated hydrochloric acid into nickel 2 plus ion complex here. Let's transfer some of this nickel 2 plus ion complex into a different boiling tube. Here we have a little bit of a concentrated nickel 2 plus ion complex. So we'll dilute it by adding a little bit of water. Now I'm going to add dilute ammonia here. Dilute ammonia, when it reacts with nickel 2 plus ion present in this aqueous medium, we are expecting to see nickel hydroxide being formed, which is going to be a green color precipitate. Now I'll be adding dilute ammonia here. As you can see, when you add dilute ammonia here, the entire solution became cloudy due to the formation of nickel hydroxide precipitate. So this precipitate again is a very fine particle precipitate, so you do not necessarily see the precipitate accumulating at the bottom just yet. If you leave it out for a while, on standing you will see the precipitate settling at the bottom, and you will be able to see the precipitate clearly then. So let's mix it first to see the actual pale green color. Now we will compare it against a white color background to see the pale green color precipitate a little bit clearly. We know that nickel hydroxide, when treated with concentrated ammonia, dissolves in concentrated ammonia and forms a deep blue color solution. Let's observe that next. In order to do that, let's take a little bit of our nickel hydroxide suspension here into a different boiling tube. and we will add concentrated ammonia onto this nickel hydroxide. We are expecting to see a deep blue color complex being formed, which is going to dissolve this precipitate that is already here. And you can very clearly see all of the precipitate that was present earlier on completely dissolved and formed a deep blue color solution over here. Since we used a fairly dilute solution, the color that we see here is a little bit pale, but still it's a deep blue color solution that we're expecting to see. We will treat it again with a little bit of concentrated ammonia so that I can show you the deep blue color that we are expected to see. Let me add a little bit more nickel nitrate into this in order for me to show you the deep blue color, which is not as diluted as this color. I will be making a little bit of a concentrated nickel nitrate solution. By adding a little bit of nickel nitrate solid into it and then dissolving in a little bit more water. Now I will transfer some of the more concentrated nickel nitrate into a different boiling tube, like so, and I will add concentrated ammonia onto this. Let's see if we can see our deep blue color solution being formed. Now we can clearly see the blue color that we are expected to see. This is a nickel ammonia complex. One nickel 2 plus ion forms a complex with 6 NH3 ligands, forming hexaamine nickel 2 ion complex. We'll put it away now. Finally, let's take our nickel 2 plus ion solution, and then we'll transfer a little bit of it into another boiling tube. Here we are going to react this with concentrated hydrochloric acid. So here we have concentrated hydrochloric acid. You have to be very careful when you're handling it. So we will be adding a little bit of concentrated hydrochloric acid into this solution. We would need a little bit of concentrated hydrochloric acid here. We would not initially see the color change. So we will have to transfer a little amount of this solution that we have formed here onto another boiling tube. And then we'll add more hydrochloric acid until we see the expected color. As you can see, now we are seeing a yellow color. Let me show it to you compared to a white background, how it will look. So compared to a white background, you are going to see a yellow color solution. Here what you have is a nickel 2 plus ion forming complex with 4 chloride ions forming NiCl4 2 minus complex ion, and that ion solution is going to be yellow in color. In summary, today we looked at nickel 2 plus aqueous ion complexes color. Over here you can see when Ni2 plus is forming a complex with 6 water ligands, what the color would be? You will see a green color solution being formed. Then we took a little bit of the nickel 2 plus ion complex, aqueous ion complex, and we added a little bit of ammonia onto it. Upon addition of ammonia, you see a formation of a green color precipitate. You can very clearly see here the green color precipitate is now starting to settle down, as it has been a while since we did this experiment. We transferred a little bit of nickel hydroxide precipitate that was formed here onto another boiling tube, and then we added concentrated ammonia onto it. Upon addition of concentrated ammonia, we saw the formation of a deep blue color solution. In this solution, we have 1 nickel 2 plus ion forming a complex with 6 ammonia ligands. Over here, we have nickel 2 plus reacted with a concentrated hydrochloric acid. So we took a nickel 2 plus ion solution, we added concentrated hydrochloric acid onto it, and we formed a complex that is yellow in color. So here, 1 nickel 2 plus ion forms a bond with 4 coordinate bonds with 4 chloride ions, forming NiCl4 2 minus ion complex, which is yellow in color. That will be all for the nickel 2 plus ion complexes. Let's move on to cobalt. Students, now let's take a look at cobalt. We have here cobalt nitrate solid. We are going to make a cobalt nitrate solution, or in other words, CO2 plus ion solution. We are going to take a little bit of cobalt nitrate solid into a boiling tube like this. And then I'm going to take a wash bottle, and we can add a little bit more water into this and dissolve the cobalt nitrate solid we have here. As you can see, we are forming a pink color solution. Let me dissolve all the solid that is present here first. There's still a bit more solid left. And here we have formed a pink color cobalt 2 plus ion solution. Here in this cobalt 2 plus ion solution, we have 6 water ligands forming coordinate bonds with 1 cobalt 2 plus ion, forming hexa aqua cobalt 2 ion complex. Let's take some of this cobalt 2 plus ion solution into another test tube so that we can react it with a little bit of dilute ammonia. We have our dilute ammonia here. We are expecting to see the formation of a pink color precipitate. But unfortunately, normally when you add dilute ammonia, you do not make this observation in the lab. We directly start seeing a blue color precipitate. In your textbook, you will see we are going to be having usually a pink color precipitate formed, which is cobalt hydroxide CuOH twice. But normally this precipitate will not be formed that easily in the lab environment. When you are adding ammonium hydroxide or dilute ammonia, the first observation you see is the formation of a complex where cobalt 2 plus is forming a complex with one OH minus ion, which is actually a blue color precipitate. Sometimes when you leave it out for a while, on standing it turns into a purple or pink color precipitate. So let's give it some time while we do other reactions. Now we are going to be moving on to adding concentrated ammonia and seeing what the color change would be like. Here we have concentrated ammonia, and we are going to see a yellow color solution being formed upon addition of concentrated ammonia. We are forming a little bit of a darker solution over here because of the concentration of cobalt 2 plus ions we used. So we'll dilute it a little bit in order to see the actual color, which is actually a yellowish brown color is what we are trying to observe here. So you can see here the formation of a yellowish brown color solution. This is due to the cobalt 2 plus ions forming a complex with 6 ammonia ligands forming a yellowish brown color solution. If you let it stand in air for a while, this solution will turn into a reddish brown color solution. That is due to cobalt 2 plus getting oxidized into cobalt 3 plus. When you let it stand in air, due to aerial oxidation, the cobalt 2 plus ions we have here gets converted into cobalt 3 plus, forming a reddish brown color solution. So to expedite that process, we can take a little bit of this solution and we are going to make it react with, we'll dilute it a little further, and we are going to react this solution with hydrogen peroxide. As you can see, upon addition of even the little amount of hydrogen peroxide that I added, we saw a very clear brownish or reddish brown color solution being formed. So this reddish brown color solution is formed due to the formation of cobalt 3 plus ions upon addition of hydrogen peroxide, right? So the cobalt 2 plus ions we had earlier is now converted into cobalt 3 plus, forming a reddish brown color complex with ammonia. Finally, we are going to take a little bit of cobalt 2 plus aqueous ion solution into another test tube, and we are going to add concentrated hydrochloric acid onto this. Upon addition of concentrated hydrochloric acid, we are expecting to see a blue color solution being formed here. Let's add a little bit of concentrated hydrochloric acid here, and we are expecting to see a blue color solution being formed. As you can see, students, what you see here is a blue color solution being formed upon addition of concentrated hydrochloric acid. And the fumes you see is hydrochloric acid because it is really concentrated. It's fuming due to the high concentration the hydrochloric acid has. And the blue color here is observed due to the formation of a complex with chloride ions. Cobalt 2 plus ions forms a complex with chloride ions, where 4 chloride ions are going to be forming coordinate bonds with 1 cobalt 2 plus ion. So basically the formula would be COCl4 2 minus. Now let's take a look at the summary. In summary, when it comes to cobalt, we first made cobalt 2 plus ion solution by dissolving cobalt nitrate in water. Here you can see the color of the solution is a pink color. This is due to cobalt 2 plus ions forming a complex with water molecules. Actually, 1 cobalt 2 plus ion forms coordinate bonds with 6 water molecules and forming this complex which is pink in color. And we added dilute ammonia onto cobalt 2 plus ion complex. There you see the formation of a blue color precipitate. Originally we are supposed to see a pink color precipitate, but observing this pink color precipitate is extremely difficult under lab conditions. So what you normally observe upon addition of sodium hydroxide is the formation of a blue color precipitate, where cobalt is forming a coordinate bond with 1 hydroxide ion. We have here the result of reacting concentrated ammonia with cobalt 2 plus ion solution. Upon adding concentrated ammonia, we saw the cobalt 2 plus ions forming 6 coordinate bonds with ammonia molecules, forming CO NH3 6 times 2 plus ion. This complex is yellowish brown in color. When you let this complex stand in air, due to aerial oxidation, the cobalt 2 plus ions oxidized into cobalt 3 plus ions. To expedite this process, we added hydrogen peroxide. Upon addition of hydrogen peroxide, we converted the cobalt 2 plus ions into cobalt 3 plus ions, forming a complex where cobalt 3 plus is connected to 6 ammonia ligands, and the color of that complex is going to be a reddish brown color. Finally, we took a little bit of cobalt 2 plus ion solution and treated it with concentrated hydrochloric acid, and the color that we saw was a blue color solution. This solution is formed due to the formation of a complex where cobalt 2 plus ions are forming 4 coordinate bonds with 4 chloride ions. So the formula is COCl4 2 minus. That is it for cobalt 2 plus ion complexes. And in summary, here in this practical, we looked at copper 2 plus ions, we looked at nickel 2 plus ions, and we looked at cobalt 2 plus ions, complexes they form with dilute ammonia, concentrated ammonia, and concentrated hydrochloric acid. All the questions related to this topic and more important parts, theory parts related to this topic will be discussed in our next session. Students, you had a look at how the experiment 21 was conducted in the lab. Now, in this session, we are going to be looking at how to answer some of the questions that are asked about the theory that is revolving around experiment 21. We have here a question that is asked about 3 of the ions that we have studied so far. They're asking us this following question. You are provided with a few samples of a solution containing the following compounds: copper chloride, ferric chloride, and nickel chloride. And they're asking us to prove that the following solution contains copper 2 plus ions, ferric ions, and nickel 2 plus ions. Copper 2 plus, iron 3 plus, and nickel 2 plus ions. So, how do we answer a question like this? Before answering a question like this, you have to remember the qualitative analysis of cations. And we categorize cations into few groups and we analyze them separately. And if you remember, we initially started off by talking about silver plus, mercury 2 plus, OH 2 plus, and lead 2 plus. So these ions easily precipitate out with addition of HCl. So in the first group, you see these cations precipitating out. In the second group, we have a multitude of cations precipitating out when we send hydrogen sulfide in acidified aqueous medium. So what happens here? Why do we need acidified, or why do we need to send H2S in acidified aqueous medium of these cations? So as you can see, even in a low concentration of sulfide ions, these cations will be precipitating out as sulfides. And then we have the group 3 in the presence of ammonium chloride and ammonium hydroxide. These 3 cations will be precipitating out as hydroxides, water insoluble hydroxides. And then you have H2S sent in the presence of alkaline medium or basic medium. So when you have a basic medium, or if you made the solution alkaline and then send H2S, if that medium contains any of these ions, they will precipitate out as their sulfides. The reason for this is going to be these zinc, manganese, cobalt, and nickel 2 plus ions, they form their sulfides only when the concentration of sulfide ion in the medium is high enough. So, as we know, H2S has an equilibrium in water. So, if you have a lot of OH minus ions in the medium, due to OH minus ions removing the H plus that is coming in through H2S, the equilibrium will be releasing more and more H plus as well as sulfide ions into the medium. So therefore, the concentration of sulfide ions in the medium will be much higher in alkaline medium. So when you send H2S in the presence of sodium hydroxide or in the presence of ammonium hydroxide or in alkaline medium, you will have a higher concentration of sulfide ions in them. So in the presence of higher sulfide ion concentration, zinc, manganese, copper, cobalt, and nickel, these 4 cations will form their sulfides. Now, so the question asks, how can we identify or prove that these ions are there? So you can very clearly see over here, if you paid attention, you would see that copper 2 plus ions are precipitating out in the second group. So if you take this solution and add dilute HCl to acidify the solution and then send H2S through the solution, what happens is copper 2 plus will react with the sulfide ions in the medium and will form copper sulfide, a black color precipitate. So copper will be removed from the medium separately. And then this will be a good indication that the copper 2 plus ions are present, because they say these are the ones that are there in the medium, and you need to separately identify them or separate them you need to separate them at different stages to identify that these actually are the ions that are present in the medium. So if you form a black color precipitate when H2S is sent in acidic medium of this solution, that means copper 2 plus ions were present there. And then we have Fe3 plus ions. Fe3 plus ions can be removed from the medium by addition of ammonium chloride with ammonium hydroxide. So when you add ammonium chloride and ammonium hydroxide to this solution, after the copper sulfide precipitate was removed, you would notice a red-brown precipitate would be formed. This precipitate is ferric hydroxide. In the presence of ammonium hydroxide and ammonium chloride, you would see iron hydroxide or ferric hydroxide, which is a red-brown precipitate being formed. This will be indicative of the presence of Fe3 plus ions. And then we have nickel 2 plus, which is going to precipitate out in the fourth group of this cation analysis. So in this fourth group, you have to make the solution more alkaline, and then you have to send H2S through it. So when you're sending H2S through it, you would note that nickel sulfide is going to be formed as a black color precipitate. So these three tests would indicate the presence of copper 2 plus, Fe3 plus and nickel 2 plus ions. So the steps would be, initially you have copper 2 plus ions in the medium, Fe3 plus ions in the medium, as well as nickel 2 plus ions in the medium. If you send H2S through this solution when the solution is acidified with HCl, you would see that the copper that you have over here is going to precipitate out as copper sulfide, a black color solid. And Fe2 plus and nickel 2 plus will still remain in the medium. If you want to identify the presence of, actually it's Fe3 plus, if you want to identify the presence of Fe3 plus, you can take ammonium hydroxide and ammonium chloride. So if you add ammonium hydroxide and ammonium chloride to the solution, you would see in the presence of hydroxide ions, Fe2 plus will precipitate out as ferric hydroxide, which is red-brown. And then the only thing that is going to be remaining in the medium as an ion is going to be your nickel 2 plus ions. Nickel 2 plus ions can be identified very easily by sending H2S after making the medium alkaline by the addition of ammonium hydroxide. After making the solution alkaline, if you send H2S through the medium, you're going to see nickel sulfide, a black color precipitate being formed. So this is how you would prove the presence of these ions, Cu2 plus, Fe3 plus and nickel 2 plus ions in the medium. Now let's move on to our next question. A salt dissolves in water to produce a colorful solution. As you know, transition metal cations, when dissolved in water, produces colorful solutions. So we could be talking about a transition metal cation producing a colorful solution here. And then when sodium hydroxide is added, it produces a light green color precipitate. Now, we have learned in the past that there are few transition metal cations that can produce light green color precipitates. And over here we have a few of them. Nickel 2 plus, iron 2 plus or ferrous ions, and we have chromium 3 plus. All three of them actually produces green color precipitates. Fe2 plus of course produces a light green color precipitate that is normally referred to as dirty green color. And then nickel 2 plus and chromium 3 plus produces green color precipitates. So now we have realized cobalt 2 plus and ferric 3 plus or Fe3 plus is not a part of the answer set. So we have to choose from these three answers. But this particular statement only bring us to these three answers. We have to have more information to figure out of these three which one is the correct answer. Then in the next sentence they say when ammonium hydroxide is added, the precipitate dissolves and produces a blue color solution. The precipitate dissolves and produces a blue color solution, and they're asking what is the cation in the salt initially dissolved in water. So they want to know the cation that was present in the salt. So if in the presence of excess ammonium hydroxide, if the precipitate is dissolving, then we have actually narrowed down what the answer is, because only these few elements, cobalt 2 plus, nickel 2 plus, copper 2 plus and zinc 2 plus, these four ions, normally cobalt, nickel, copper and zinc are the last four elements that are found on the 3D elements. So these four ions are the ones that will produce a precipitate first when ammonium hydroxide is added, and then if excess ammonium hydroxide is added, those precipitates will dissolve to form colorful solutions, with a small exception of zinc 2 plus. The precipitate that is initially formed is going to be white in color, and the solution that is formed on addition of excess ammonia or excess ammonium hydroxide is going to be colorless. However, the precipitate will dissolve to form a colorless solution. So these elements will produce a precipitate first upon addition of ammonium hydroxide or sodium hydroxide for that matter. But if you add ammonium hydroxide, they will produce a solution. Now, after realizing only these are the cations that will form a precipitate first with ammonia and then dissolve in excess ammonia, we have an understanding what the answer is. Answer is going to be the second option that we have here. So nickel will be our answer. Answer is going to be nickel. Why? Because nickel is the only cation over here that will produce a hydroxide that is insoluble in water, that is green in color, and then will dissolve upon addition of excess ammonia. So nickel hydroxide is a green color precipitate, but if you add excess ammonia or ammonium hydroxide to it, it will dissolve to form a blue color solution. So therefore nickel is going to be your answer. So all the other answers that we have over here are going to be disregarded, as Fe2 plus doesn't dissolve as Fe2 plus does not form a precipitate that will dissolve in excess ammonia, and nor will chromium 3 plus. So the answer is 2. Now we have come to our third question. In the third question, they are asking that there is A, B and C, or we'll read the question first. A, B and C gives precipitates when reacted with ammonium hydroxide. This precipitate dissolves in excess ammonium hydroxide, so therefore identify A, B and C. We just spoke about the cations that produce precipitates that dissolve in excess ammonium hydroxide. What are those cations? We remember the last few elements of the 3D elements. Cobalt 2 plus cation, nickel 2 plus, copper 2 plus, and we have our zinc 2 plus. When these cations are reacted with ammonium hydroxide, they form precipitates. So, as we saw earlier in our experiment, cobalt, when reacted with a little bit of ammonium hydroxide, it gave a blue color precipitate. But if you manage to obtain cobalt hydroxide without obtaining this blue color complex, then you will see a pink color precipitate. However, in the lab environment, we noticed upon addition of ammonium hydroxide, the precipitate we obtained was blue in color. And then we have nickel. Nickel, when reacted with ammonium hydroxide, will produce a green color precipitate. These are the precipitates that are getting formed, so we'll call it PPT. Blue color precipitate, a green color precipitate, and then copper will produce a pale blue color precipitate. And we have zinc that is going to produce zinc hydroxide, which is white. So these are the colors of the precipitates that they form. So cobalt, blue, nickel is going to produce a green color precipitate, copper is going to produce a pale blue color precipitate, and zinc is going to produce a white color precipitate. And then if you dissolve all of these, or if you add excess ammonium hydroxide, these precipitates that are formed will dissolve to form solutions. So these solutions are formed due to the cations forming a complex or coordination complex that is soluble in water. So green color precipitate will dissolve of nickel 2 plus. It will form a dark blue color solution, and this blue color cobalt precipitate will dissolve to form yellow brown solution, and this blue color, pale blue color precipitate will dissolve to form a dark blue color solution, and the white color precipitate will dissolve to form a colorless solution. So these are the observations when you try and dissolve the precipitates that are formed through addition of ammonium hydroxide to these cations. And these precipitates that are formed are dissolved in excess ammonium hydroxide to form these colorful solutions, with the exception of course, zinc 2 plus. Zinc 2 plus is not a transition element, so therefore the zinc hydroxide that is produced as well as the solution that it produces afterwards is going to appear colorless. The precipitate will be white, but the solution is going to be colorless. So that brings us to the understanding that we are mainly talking about these four cations: cobalt, nickel, copper, and zinc. And then we have to understand what else is present here. The very first answer, it has copper 2 plus and nickel 2 plus, which are actually forming a precipitate and then dissolve in excess ammonium hydroxide. But chromium 3 plus ions actually do not dissolve in excess ammonium hydroxide. In fact, actually, chromium dissolves normally in sodium hydroxide. So if you take chromium 3 plus ions and if you react it with hydroxide ions, you are going to get chromium hydroxide, which is a green color precipitate. However, if you try to dissolve it in excess ammonia, or ammonium hydroxide, there won't be any reaction taking place. But when you try to dissolve it in excess sodium hydroxide, then at that point it produces this complex CrOH 4 times 1 minus. Due to formation of this coordination complex, this green color precipitate will dissolve in excess sodium hydroxide, but that will not happen with excess ammonium hydroxide. So chromium, of course, is not going to be an option. So therefore, the very first answer is not the solution. If you take a look at the second answer, copper and nickel again are answers, however, aluminium is not. And why isn't aluminium an answer? Although aluminium reacts with hydroxide and produce a precipitate like this, although a precipitate is formed with aluminium, this aluminium does not actually dissolve in excess ammonium hydroxide. Just like chromium 3 plus, this aluminum hydroxide also dissolves in excess sodium hydroxide, not excess ammonium hydroxide. So aluminium is also not a part of the answer. And then we have zinc, copper and nickel in this answer. So you will see zinc, copper and nickel, all three are present here in the solution set where you see that forms a precipitate upon addition of ammonium hydroxide, but also upon addition of excess ammonium hydroxide, that precipitate dissolves to form a colorful solution. Again, I would like to remind you, zinc being the exception. Zinc does not produce colored precipitates, or it does not produce any colorful solutions. However, it does produce a precipitate that is white, that dissolves upon addition of excess ammonium hydroxide. And later on, you realize this contains all the cations that fit this description. So the answer is going to be 3. However, let's take a look at why 4 and 5 are not answers. So when it comes to question number, answer number 4, chromium is there. Zinc and copper are parts of the answer, but chromium is not going to fit the description of this question, so therefore chromium is out. And over here we have aluminium. But why didn't I take silver? Silver, although is not a member of these 4 cations that I mentioned here, silver does actually form a precipitate that dissolves in excess ammonium hydroxide. Upon addition of, now if you take silver 1 plus and upon addition of hydroxide ions, or upon addition of ammonium hydroxide, it produces silver oxide. This silver oxide can be dissolved in excess ammonium hydroxide. If you add excess ammonium hydroxide, it produces this complex. Due to formation of this complex, silver ions will actually be a part of the answer for this question. Why? Because silver ions will form a precipitate. It is not a hydroxide that is formed, it is an oxide that is formed. However, the question says a precipitate is formed, and then that precipitate is going to be dissolved in excess ammonia. Which happens? Actually, this is going to be your tolerance reagent. When you are carrying out experiments to identify aldehydes and ketones, you'll be using tolerance reagent. And this is the formula of tolerance reagent. So, although silver is part of the answer, we can actually reject the 5th answer as well due to the presence of aluminium. Aluminium does not fit the description. So, the answer would be 3. Now, let's move on to the next question. Let's take a look at the 4th question. What statement is true about zinc, copper, and nickel? Zinc, copper, and nickel. So let's take a look at the very first statement. All are transition elements. Now students, in the beginning of this experiment, in the theory part, we discussed what a transition element is. Transition element is an element that has, or element or an ion that will have incompletely filled d subshells in them. However, we can see over here zinc is there. In the 3D elements, zinc is not considered to be a transition element. All the elements from scandium to copper is considered transition elements. However, zinc is not considered a transition element. It is a 3D element, however, it is not transition. So therefore, this statement is wrong. And they are saying zinc, copper, and nickel, their ions form coordinate complexes with aqueous ammonia. Their ion forms coordinate complexes with aqueous ammonia. True. We saw that cobalt, nickel, copper, and zinc, in the previous question as well, we saw they were able to produce hydroxides that are precipitates, and then if you add ammonium hydroxide or concentrated ammonia to those precipitates, we saw them dissolving. Why did the precipitates dissolve? Due to the formation of a complex between the cation and ammonia. So because of that, we are going to have this also as a correct answer. The ions form coordinate complexes with aqueous ammonia. Actually, we looked at cobalt, nickel and copper's ammonia complexes and their formulas in the theory part as well. So this is correct. Their oxides are quite colorful. Again, we don't have to even dive much further because we very clearly know zinc is not producing any oxides that have a color. So therefore, without any hesitation, we can actually take this statement as a false statement because zinc does not produce any colorful oxides. 2 plus is a charge of the more stable ion they form in aqueous medium. Yes, you would observe in all of their aqueous mediums, you will have the 2 plus charge as the most stable charge that they have actually acquired in aqueous medium. So all of the cobalt, nickel, copper and zinc, and if you take the aqueous solutions, you would observe what they have in their aqueous solutions is these ions, 2 plus ions. So therefore, that statement is also correct. In aqueous medium, the 2 plus charge or 2 plus ionic stage is the most stable. So therefore, the correct combination is B and D. So B and D solution isn't here in the first 4 answer sets. So therefore, the answer for this question is going to be 5. Any other number of responses are correct. So B and D are the correct responses. So therefore, we have to choose 5 in this MCQ. Now, let's have a look at the 5th question. A, B and C are aqueous cations. They react with H2S in aqueous medium and form precipitates. So H2S in aqueous medium and forms precipitates. That's the first statement. And in the second one, they say form precipitates when reacted with ammonia, and these precipitates dissolve in excess ammonium hydroxide. By now, it has to be your favorite question because why? We know the cations that form a precipitate when ammonium hydroxide is added, and we know which cations actually dissolve the precipitate that they formed in excess ammonia. So the transition metal ions that fit into this description are well known to you now. It is cobalt 2 plus, nickel 2 plus, copper 2 plus and zinc 2 plus. And now we have to, apart from that, there's another requirement. They're asking what A, B and C cations are, and all of these cations should be like, one of these 4 cations, but at the same time they have another requirement to fulfill. That is, they need to actually be able to produce a precipitate with H2S in aqueous medium. So we know that there are 2 groups in cation analysis that we observe that produces precipitates with H2S. If you observe the group 2 and group 4, we can see we are using H2S in an aqueous medium that produces a precipitate, but the conditions are somewhat different. In group 2, although H2S is producing a precipitate with some of these cations that we have here, the solution needs to be acidic. And in group 4, the solution is alkaline. However, keep in mind, we make the solution either acidic or alkaline to either decrease the concentration of sulfide ions in the medium or to increase the concentration of sulfide ions in the medium. When the solution is acidic, the concentration of sulfide ions in the medium are quite low. But when the solution is alkaline, the concentration of sulfide ions in the medium are quite high. So these cations that we have here, like zinc, manganese, cobalt and nickel, actually require higher concentration of sulfide ions for them to make a sulfide as a precipitate. But all of these cations would precipitate as sulfides even in lower concentrations of sulfide. So cations in both of these groups, group 4 and group 2, are actually qualifying for this description, for the first description. However, only a few actually qualifies for the second description. So if you take a look at zinc, copper and barium, we can see zinc and copper can be found in the fourth and the second group. Zinc is present in the third group and copper is present on the second group. So those two actually fulfill the first statement as well as the second, because we can see all the elements that fulfill the second statement is written here. Right, so we can see that zinc and copper are found in both of these places, but barium isn't. So because of the presence of barium in this answer, we can reject the answer number 1. In the second answer, you're going to see zinc, copper and nickel. Now zinc, copper and nickel actually fulfill the second statement. You can see all the elements fulfilling the second statement are written here, and zinc, copper and nickel are fulfilling that. At the same time, you can find zinc, copper and nickel in group 2 and group 4 as well. Or as told previously, we remember that group 2 and group 4 contain the cations that can form precipitate in the presence of aqueous hydrogen sulfide. So therefore, copper 2 plus, zinc 2 plus and nickel 2 plus fulfill the first statement as well. So therefore, the answer is actually this. But let's take a look at why all of the other answers are incorrect. So the answer for this question is 2, but let's move on ahead and try to find out why the other answers are incorrect. So in the third answer, there's aluminium. Aluminium is not found in these 4 cations, which means based on that we can reject the third answer. When it comes to the fourth answer, again we can see aluminium, right? Aluminium cannot be considered whenever it is present in the answer set, because aluminium is not present as a precipitate that dissolves when excess ammonium hydroxide is added. At the same time, it is not something that is going to be found in either group 2 or group 4. So therefore, aluminium has to be rejected. And on the fifth one, we can consider chromium. And chromium also does not form a precipitate that dissolves in excess ammonia. So therefore, because of that, chromium is not an answer. So fifth solution set will also not be the correct answer. The correct answer is going to be the second answer. Now, let's move on to the next question. A water sample contains a metal ion. When sodium hydroxide was added to the sample, a gelatinous green precipitate was formed. When ammonia is added, the precipitate dissolves to form a dark blue solution. When hydrogen sulfide is sent through the acidified sample of the solution, no precipitate was formed. What is the cation present in water? So these are the most important points that we are going to highlight. That they initially mentioned that this is the metal ion that we are concerned about, and upon addition of sodium hydroxide, it formed a green precipitate, a gelatinous green precipitate. And upon addition of ammonia or excess ammonia, this precipitate dissolves to form a dark blue color solution. At this point, students, you should remember what are the cations that are going to be producing a green color precipitate when it comes into contact with hydroxide ions, and what precipitates actually dissolve in excess ammonia. So in this case, we know there's only a few cations that produce a precipitate and then dissolves the precipitate in excess ammonia. Those are cobalt 2+, nickel 2+, copper 2+, and zinc 2+. And apart from that, we do know a cation that produces a green color precipitate and then dissolves in excess ammonia to produce a dark blue color solution. If you guessed nickel 2+, you are correct. So based on just that, we can actually select nickel 2+. However, we are not done yet. There's another part. When H2S is sent through an acidified sample of the solution, so acidified gets extra emphasis because that is key in this answer. Acidified sample of the solution, no precipitate was formed. So where in the analysis groups do we send hydrogen sulfide in acidified solution of a sample? Actually, in the second group. If you take a look at the second group, there are few elements or few cations rather that form sulfide precipitates when you send H2S in the presence of HCl, or after making the solutions acidified. If you send H2S, these cations are going to be forming precipitates. But the condition mentioned in this question is the cation that we are talking about do not form a precipitate. So the cation that we are suspecting is nickel 2+. That is, we consider that to be the answer that is fitting in with the other points of the question. So we can't, or we should not be able to find nickel 2+ in group 2. And in fact, we don't. We don't have nickel 2+ in this answer set. Meaning, nickel 2+ is our answer. However, keep in mind that nickel 2+ will precipitate with H2S in alkaline medium. And they are talking about acidic medium here. So if the question said alkaline medium, then nickel 2+ will not be an answer. However, since they are bringing up acidic medium, our answer is nickel 2+. And now let's talk about why chromium can't be an answer. Because you know chromium 3+ will also first produce a green color precipitate. So chromium, although it produces a green color precipitates, it will not dissolve in excess ammonia. And it will not make a dark blue color solution dissolving that chromium hydroxide precipitate. So therefore, chromium is not going to be considered an answer or an answer to this question. So the answer is nickel 2+. Now let's move on to the next question. 7th question. Which cation forms a blue color solution with excess ammonium hydroxide? So there are a few cations given here. Which one forms a blue color solution with excess ammonium hydroxide? Does not produce a precipitate when acidified with HCl and reacted with hydrogen sulfide. So it says does not produce a precipitate, and produces a yellow-brown solution with concentrated HCl. So again, Students, you have to keep in mind the colors of the precipitates or solutions that are normally getting formed when it comes to the transition elements. Forms a blue color solution with excess ammonium hydroxide. So there are two transition elements we looked at in this experiment that produced blue color solutions with excess ammonium hydroxide. What are those two ions? We saw copper 2 plus ions. First, when you add ammonium hydroxide, it forms a pale blue precipitate, and then if you add excess ammonium hydroxide, it forms a dark blue color solution. The other ion was nickel 2 plus. When added with a little bit of ammonium hydroxide, it forms a green color precipitate, but if you add extra or excess ammonium hydroxide, that precipitate dissolves and forms a blue color solution. So they are saying it does not produce a precipitate when acidified and reacted with H2S. So after figuring out that our possible answers are going to be either copper 2 plus and nickel 2 plus, we need to narrow it down to one answer. So the second statement helps us with that. It does not produce a precipitate when acidified with HCl and reacted with H2S. We saw on an earlier question as well, if you go back, we saw the group 2 in the cation analysis groups is the group that produces precipitates when H2S is sent in an acidified solution. So in this cation group, we do not find nickel 2 plus. Instead, however, we do find copper. So copper 2 plus is going to be an ion that can get precipitated out if you acidify the solution and then send H2S through it. So if copper 2 plus ions are present, at that point a black color copper sulfide precipitate will be formed. But the statement over here, the second statement says the cation actually does not form a precipitate when you acidify the solution and react it with H2S. So therefore we cannot consider copper 2 plus. We can only have nickel 2 plus as the answer. Copper 2 plus cannot be considered. So now by this point we have already obtained our answer. Now the last one or last statement will confirm our answer. Produces a yellow-brown solution with concentrated HCl. Yes, true. Nickel when reacted with concentrated HCl, nickel 2 plus will form a complex ion NiCl4 2 minus. So this complex ion is going to be yellow in color. So therefore the answer is correct. So we have nickel 2 plus as our answer. So the answer that we have obtained is correct. Now we are moving on to the next question. Which of the following tests can be used to separately identify nickel chloride and copper sulfate solutions separately? So we have nickel 2 plus ions and copper 2 plus ions in these two solutions, nickel chloride and copper sulfate. So let's take a look at the processes that they have suggested. Addition of excess ammonium hydroxide. Will there be any way to separately identify these two? If you add excess ammonium hydroxide directly to copper 2 plus and nickel 2 plus, what are the products that are going to be formed? Nickel 2 plus ions are going to directly turn into nickel ammonia complex. which is going to be dark blue in color. And if you take copper 2 plus and add concentrated ammonia to it, you're going to get the same observation. You're going to get copper NH3 4 times, or copper ammonia complex, which is also dark blue in color. So you can't use addition of ammonium hydroxide to find out whether you have nickel 2 plus ions or copper 2 plus ions, or you can't use it as a test to separate the two solutions. So addition of excess ammonium hydroxide directly is not going to be a useful test to identify these two solutions separately. What about addition of concentrated hydrochloric acid? That also will not be a useful test. Why? As we know, addition of concentrated hydrochloric acid obviously cannot be used to identify these two solutions separately, because nickel 2 plus is going to be producing a complex with chloride ions and form a yellow color solution. And the same color can be obtained if you add hydrochloric acid or concentrated hydrochloric acid to a copper 2 plus ion solution. So the copper 2 plus ions will form a coordination complex with HCl or Cl minus ions and will form a yellow color solution. So both nickel 2 plus and copper 2 plus will form a yellow color solution when reacted with concentrated HCl. So those two are not going to be considered answers for this question, but you can actually use the third one to separately identify these two solutions. So actually the answer would be the third one. So let's see why that is. So if you take copper 2 plus and react it with sulfur dioxide, addition of sulfur dioxide, copper is going to get reduced to copper 1 plus. So from cupric to cuprous. So copper 2 plus ions are pale blue in color, or copper 2 plus ion solutions will appear pale blue in color, but copper 1 plus is going to be colorless. So therefore this is going to give us a color change. Sulfur dioxide is going to turn into sulfate ions. Of course, it does not interfere with any colors. However, this is going to be able to change the color of the copper 2 plus ion solution. Can the same be done to nickel 2 plus ions? If you take a nickel 2 plus ion solution, which is green in color, and if you add sulfur dioxide, if you try to react it with sulfur dioxide, there won't be any reaction taking place. There won't be any nickel 1 plus formed while sulfur dioxide oxidizes to sulfate ions. So there aren't any products formed when you are reacting sulfur dioxide with nickel 2 plus. So reacting with sulfur dioxide can be a reaction that can be used to identify the copper 2 plus ion solutions and nickel 2 plus ion solutions separately. So the answer for that question is 3. Then we have adding excess ammonium hydroxide when reacting with H2S. Now you can see, we saw earlier also that copper 2 plus is found in the second group of cation analysis, and nickel was found on the fourth group. That means copper 2 plus will form precipitate if H2S is sent through an acidified solution of copper 2 plus. And when it comes to nickel 2 plus will form a precipitate if H2S is sent through an alkaline solution of nickel 2 plus. So what this means is that both of them are capable of forming a precipitate with H2S. Copper is capable of forming a precipitate with H2S even in very small concentrations of sulfide ions in the medium. Nickel 2 plus, however, needs an alkaline medium, meaning at that point you have a higher concentration of sulfide ions. So when the statement says adding excess ammonium hydroxide and reacting with H2S, what we are creating is a medium that has enough and more sulfide ions or higher concentration of sulfide ions that will allow both copper 2 plus and nickel 2 plus to form precipitates. Of course, copper 2 plus is very easy to precipitate out as a sulfide because it requires only a small amount of sulfide ions. That is why you find copper 2 plus in the cation analysis group 2. But nickel 2 plus requires an alkaline medium because it requires a higher concentration of sulfide ions. So since we have provided an alkaline medium and then sent H2S through the medium, it indicates both of these ions can be precipitated out with the help of H2S. Now, then we have dropwise addition of silver nitrate. Silver nitrate is going to be able to precipitate in the presence of chloride ions. So we have a nickel chloride solution here. So if you take nickel chloride solution, it will contain nickel 2 plus ions along with chloride ions, and when silver ions are coming into the medium, it is going to be able to come into contact with the chloride ions and will form silver chloride, which is a white color precipitate, white color water insoluble solid. So this will be an observation when silver ions comes into contact with chloride ions. How about copper sulfate? If you take copper sulfate, you have copper 2 plus ions in the medium and sulfate ions in the medium. And when silver ions are added to it, if now we are adding silver ions drop by drop, although silver sulfate is fairly soluble in water, it is not extremely soluble, but it is considerably soluble in water. Silver sulfate, if you continue to keep adding silver 1 plus ions to the medium, at one point the concentration of silver ions will be high enough for it to form a precipitate with the sulfate ions present in the medium. So after the Ksp value reaches a specific threshold, you would see that the silver ions concentration would be sufficient enough at that point to form silver sulfate precipitate. So this silver sulfate precipitate is going to be also a white color precipitate, just like the silver chloride white color precipitate. So this cannot be used to identify the two solutions. One solution is nickel chloride. If you add silver nitrate to it, it will produce a white color precipitate. And while dropwise adding silver nitrate to copper sulfate solution, at one point it will form a precipitate which is also going to be a white color precipitate. So this cannot be used to identify the two separate solutions. Let's move on to our next question. In this question, they're asking us to find out the formula of a complex. So they say there is a complex of cobalt. The cation is cobalt 3 plus, so they have given you the charge, and they are saying in 1 mole of this compound, there are 5 moles of ammonia and 1 mole of cobalt, and this complex also contains 1 chlorine. So they are saying 1 cobalt, 5 ammonia and 1 chlorine is actually found in this complex. They're asking you for the formula of the complex. So students, first of all, we'll take a look at all of the ions and ligands that are present here in this particular compound or complex. So we have cobalt, 3 plus ion, and then we have ammonia. Actually, how many of them? There are 5 of them. So, and ammonia normally as a ligand, it has a name, amine. When you write amine, there will be 2 M's, and you can see the lone pair that it normally used to donate to the central metal ion, and there's 1 chloride ion. So this is going to be normally referred to as chloro, and sometimes even in certain other scientific literature you might find chlorido. So when you are writing a formula, you have to make sure the ligands. Now initially we indicate the cation, and then after that the ligands. Normally the ligands are written in alphabetical order. After A only C will be found when you are using the alphabetical order. So therefore, when you write this formula, you will indicate the cobalt metal first or metal ion first, and then there will be 5 amine groups. So you put the bracket normally to indicate 1 unit of ammonia, and then outside of the bracket the number 5 is there to say this complex contains 5 of those amine ligands. And then we have the chloride ligand right next to it, because when it comes to our alphabetical order, the name amine comes first before chloride, or chlorido in this case. So now, after writing the formula, you need to come up with the charge. So the cobalt ion that we had over here was 3 plus in charge. What about the chloride ion? 1 minus. Ammonia didn't have a charge. So therefore, the overall charge is going to be 2 plus, right? So 3 minus and 1, so 3 plus and 1 minus will cancel each other's charges to an extent and will produce an overall 2 plus charge. After doing that, you can then write the full formula by attaching chloride ions to this complex ion so that you can make a coordination compound. So we have, since the charge is 2 plus, it would require 2 chloride ions to attach to this complex ion to finalize the formula. So the final formula, according to our calculations, is this. And the answer containing that formula out of all of the 5 answers is this, the first one. So the answer for this question is the first answer. Students, with that we come to a conclusion when it comes to discussing past paper questions, and we will conclude the experiment 21 here. And I hope that you have developed a really good understanding about the chemistry that is revolving around the experiment 21. We mainly looked at cobalt, nickel and copper and their charges, the colors of their aqueous ion solutions, what takes place when we react them in ammonia, and then what takes place when you react them in HCl. We looked at all of that in this experiment. So I'll meet you again in the next experiment.